After last night's cloud cover, thankfully the sky is completely clear tonight. The stars are out and Jupiter is shining.
Yes, last night we searched for evidence of life on other worlds. Tonight we're going to try and explain how everything came to be here in the first place just by looking up at the night sky.
That's right, we've got 1 hour to tell you the entire history of our universe, so hold on to your hats, because by the end of this programme, Brian's going to try and answer the question more of you have asked him than anything else. What happened before the Big Bang?
Yes, I'm Brian Cox, he's Darragh O'Brien, and this is Stargazing Live.
Welcome back to Jodrell Bank. Yes, we were very unlucky with the weather last night. The minute we stopped the show, the clouds opened. Astronomy, it's all about timing. Yeah. This is the second night of stargazing. Thank you so much for all of your questions and photographs that you've already sent us. The sky's cleared and we have been inundated.
Yeah, there are some incredible images that you've sent in. Here's the first one. I think it's a beautiful image of Jupiter and Io. Now, this was taken actually using an 8-inch refractor. So it's last night. So it's a beautiful image. And this one, from the Milky Way over Trusk Loch.
Yes,
on the goal, down your way.
Fantastic.
That's by Brendan Alexander, again taken last night. And finally, I think this is a beautiful picture. This is the Flame Nebula in Orion, wow. Which is it's an object that you can see. You see Betelgeuse in Orion, and then the star in the belt nearest to Betelgeuse is just below there. That's actually the star that lights up this nebula. And there's dark patches there, dust lanes across the glowing gas. So beautiful image.
Fabulous stuff. We do want to see more of these, more questions, more photographs. We'll cover them in this show or in the later show that we do, Stargazing Back to Earth. Email them to us, stargazing@bbc.co.uk. Send them to us on Twitter, to our account @BBC Stargazing, or go to our website, bbc.co.uk/stargazing, where you find details of over 500 Stargazing live events taking place all over the country, and where cosmologist Ed Copeland is waiting to join in with our live web chat as well.
I bet you say that in your sleep, don't you?
Do we do
you
the
like
web
that?
desk, the web desk.
Send in some
bbc.co.uk.
Anyway, tonight we're going to try and take you on a tour of the history of everything. Now take a look at this image. This was taken by the Hubble telescope, so the telescope in orbit around the Earth. And in this image, there are some of the most distant galaxies we've ever seen. In particular, the interesting one is this one. So it's got an 11.9 next to it. You can't see it there, very, very faint. But this is an image of that galaxy. Now that is 13.35 billion light years away from Earth. That means that light has taken 13.35 billion years to travel from that into the Hubble Space Telescope. The universe, as we'll find out later, is only 13.75 plus or minus 0.1 billion years old. A spectacular measurement in itself. So that light has been travelling throughout the entire history of the universe, pretty much. You've seen a galaxy there that formed only a few 100 million years or so after the Big Bang.
See, what we see is a snapshot of what that star or galaxy was like at the moment its light left on the long journey to us. Let's cross over to Mark in our dark field for a couple of other examples of what you can see.
Hey guys, it's great to be back here again with the Liverpool Astronomy Society. Say hello, gang. Well, I think they're quite cheery because we've got clear skies at the moment. It's a bit patchy, it keeps coming and going, so it's a little bit frustrating, but it's staying clear. Earlier this evening, we did manage to get some footage of the Pleiades star cluster. Now, that's otherwise known as the Seven Sisters, and it's 2.6 quadrillion, which is a million billion miles away, which means it takes its light 440 years to get to us. Now, there are about 6,000 stars that you can see with the eye from Earth, and of course most of those are in the Milky Way. There are a couple of objects which you can see which aren't in the Milky Way, so it's the Andromeda Galaxy, and we have got a live image now through one of our telescopes of the galaxy, and it's an object which is 15 quintillion, which is a billion miles away. Now that means that the light's been travelling for 2.5 million years to get to us, so the image you're seeing is just under 3 million years old. Now that means if you turn around on its head, of course, if anybody's on a planet inside the Andromeda Galaxy looking back on us, then they're seeing us as our ancestors were starting to walk on 2 legs, which is really quite a crazy concept. Great objects to look at, so try and get a look at them if you can, but for now, back to you guys in the studio.
Thanks, Mark. Do you understand those? I know quintillion, I've never heard that.
Quintillion, yeah, it's million. I'm taking a guess that I should have put the brakes on 1 million ago there, but I think it's around that.
It's about 10 to the 10 or something. Proper language.
Okay.
Anyway, so the deeper into space you can see, the further back in time you're looking.
But it isn't just telescopes down here that give us an insight into our past. A lot of our greatest questions have been answered by sending incredibly complex instruments into space. And many of the most sophisticated were built in the very room where Liz Bonin is now.
Hi guys, welcome back to NASA's Jet Propulsion Laboratory here in California. This is High Bay 1, the JPL clean room where they built Voyager, where they built the Galileo orbiter and also the Mars Curiosity rover that we saw last night. Not only that, but this is the room where the wide field planetary camera of the Hubble telescope was built, the camera that's given us the deepest view into our universe to date. Now tonight I'm going to find out how that camera has just improved on that image, and I'm also going to show you Hubble's successor, the biggest space telescope ever built. Come back to me soon.
So the telescopes in space, the radio telescopes here, the optical telescopes you have at home, they all look for light, but they just look for different types of light. The light we see is only a tiny proportion of the light that exists in the universe.
Yeah, and I'm going to expand on that idea in the old-fashioned way with a piece of chalk and a blackboard. So visible light, well, light, first you need to know, is an electromagnetic wave. It's a wave. It has a wavelength. It's a distance from peak to peak. The visible light has a wavelength of about 500 nanometers, which is, what, 500,000 millionths of a meter, so a very small wavelength. So that's visible. That's what our eyes can see. If you go to longer wavelengths, then first you move to what's called infrared light, infrared radiation. We can't see that, we can feel it. You feel it as heat. Go further to even longer wavelengths, and we go through microwaves, which have a wavelength of what, about 5 centimetres or so, depending on your microwave oven uses, and then on into the radio part of the spectrum. Jodrell, at the moment, the Lovell telescope, is detecting wavelengths of around 20 centimetres. We can have radio waves all the way out to hundreds of metres, even kilometres in wavelength. Go to the other end of the electromagnetic spectrum, the wavelengths start getting shorter and shorter and shorter. Beyond the visible, there's ultraviolet. That's the stuff that you can't see but gives you a suntan. Shorter wavelength still, we get out to X-rays, which pass through, for example, your skin, which is why you can see your bones with an X-ray. And then finally, to what we call gamma radiation, this high-energy, low-wavelength radiation at the far end of the electromagnetic spectrum.
And while the telescope you'd be most used to here would obviously be an optical telescope, which takes in light, the light we can see through our eyes, different telescopes have been designed to cover all parts of that spectrum. And we have images from them here, for example, from the Fermi Gamma Ray telescope. That's Nova Cygni, which is a constellation in Cygnus, and it's a powerful eruption. It's equivalent to 1,000 times the energy emitted by the sun.
Yeah, and this is why you're seeing super high energy photons, as it were, very short wavelengths there.
The Chandra is an X-ray telescope. That would be another star cluster, I presume, there. The Hubble is actually an optical light telescope. Yeah. These are the pillars of creation. Giant clouds of dust.
Yeah, and one of the things that's interesting is that, you see, the Hubble telescope's in orbit because visible light is one of the few pieces of the electromagnetic spectrum that's affected by our atmosphere. So turbulence in the atmosphere, clouds, of course, radio waves go straight through, which is why the Lovell can observe under cloud, which is why it works in Manchester.
Yes, so we don't actually have to put all telescopes up into space to be better. And then, of course, we've got other ones. We have microwave telescopes. This is from the Planck microwave telescope. This is a particularly good one. I like this one. This is an infrared image of the Eye of Sauron, also known as the Helix Nebula. What is that?
It is very beautiful. It's a material coming off a dying star. And in there, as we'll see later, actually, the elements of life have been spread out into the universe. That's a beautiful picture.
Collectively, these telescopes have allowed us to piece together the grand story of our universe. But first, before we tell the story, we need to try and give you a sense of timescale. When did everything start, and how long will it last? The professor here takes a boat journey to try to explain our best theories.
The rhythms of the natural world have an eternal quality to them. Perhaps that's why our earliest theories of the universe pictured it as unchanging and everlasting. But over the last century, that picture has been transformed. Our current best model of the universe, the current paradigm, if you like, is called the Big Bang model. And that says that the universe is 13.75 billion years old, which means that it began 13.75 billion years ago. So, if the universe had a beginning, does that imply that it will also have an end? To answer that, we need to understand how the universe evolves with time. That's something that was discovered in the 1920s, when astronomers measured the movement of distant galaxies relative to the Earth. If you look at the galaxies beyond the Milky Way, then what you find is that for all but our nearest neighbours, all the galaxies appear to be rushing away from us. Imagine all these dots are the galaxies, and then I blow up the balloon. What you see is that as the balloon expands, then every dot, every galaxy moves away from every other galaxy. And the interpretation of the measurement that virtually every galaxy is rushing away from every other is the same. They're doing that because the universe is expanding, and it's been doing that since the Big Bang. The cause of this expansion is not fully understood, but in the billions of years since the Big Bang, space has continued to expand. But there are also other forces at work on the galaxies in the universe. All those galaxies out there across the universe have at least one thing in common, which is that they're massive. They have mass. They're made of solid objects. Now, Isaac Newton told us that there is a force that exists between objects that have mass, the force of gravity, and it's always attractive. That means that it acts to pull things together. So if I drop this shell, then, due to the force of gravity, it meets the Earth. Think about what that means for the expansion of the universe. It's full of these galaxies, a great deal of matter, a great deal of mass, all attracting itself together. So the mass in the universe acts as a brake on the expansion. The mass in the universe acts to slow the expansion of the universe down. For much of the 20th century, scientists believed that the balance between these two effects, the initial expansion and the braking effect of gravity, would determine how the universe might end. In this old theory, if gravity won the battle, then the expansion might not just slow down, it might even stop and reverse, so the universe could one day begin to contract. That scenario is called a big crunch. It literally means that every galaxy in the sky would start rushing towards every other galaxy, and eventually the entire observable universe would shrink back to the size of a single atom, hot and dense. It would be an incredibly violent end to the universe. But just over a decade ago, when astronomers measured how space has been expanding over time, they discovered something unexpected, which completely changed how we think the universe might end. 5 billion years ago, the expansion of space actually began to speed up, as if something had given it fresh momentum. So what is this mysterious thing that's stretching the very fabric of space itself? Well, the best answer I can give you is that we don't know. It's one of the great mysteries in physics. It does have a name. It's called dark energy, and that's pretty much all that everybody can agree upon. There are theories about what this dark energy is and where it comes from, but so far, nothing quite seems to fit. What we do know is that it's present in every cubic metre of space, here and out beyond the edge of the solar system, beyond the Milky Way, and right out to the edge of the observable universe. Space contains dark energy. And the universe, as far as we can tell, will continue to accelerate faster and faster. The galaxies will get further and further away. Then ultimately, that dark energy will dominate. And our best guess is that the universe will continue to accelerate in its expansion forever.
We've lots and lots of questions, by the way, coming in. Loads of people have asked a version of this one. Bob from Taunton, Cormac from London, various people asking, how do we know the universe is expanding?
It's one of the most important measurements in astronomy, first done by the great Edwin Hubble, as we'll see later, back in the 1920s. If you look out to distant galaxies, and you can pick out stars in those galaxies, then what you see is that they emit light, but that light is stretched. And what you find is that the further away the object is that you look at, the more stretched the light is. How do you measure the distance? Well, there are certain objects, supernova explosions, or particular types of them, for example, where we know the brightness. We understand the physics well enough to know how bright it should be, and then it's quite simple. You look at how bright it looks, and you can work out the distance. So we can measure the distance to distant objects. We can look at how stretched the light is, and that tells us that the universe has been stretching. I mean, imagine a wave of light that's been travelling from some object for 1 billion years. The universe has been stretching for 1 billion years, and so the light will have been stretched 2 billion years away, 2 billion light years away. It'll be stretched more because it's 2 billion light years away rather than 1 billion. And so by that process, you can map the expansion of the universe.
And then if you run the clock backwards, you start drawing it in, and as we go backwards in time, it reduces down the universe.
Well, that's it. So you just reverse it mentally. The universe is contracting, 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 and at some point you find that everything was on top of everything else. That is what we call the Big Bang, and that's what we're going to be talking about later on.
Okay, we have a Year 5 class teacher called Lucio Polly here who asked a question on behalf of our class. How can space never end?
How can space never end? It's a very difficult concept. What I can tell you, though, is if indeed it never ends, if the universe is infinite now, then it has always been infinite. It was born infinite. So I hope that is the answer.
Yeah, that's solved it. That's settled it, all right? We're happy with that answer? Yeah, Year 5?
Yeah, absolutely.
Yeah.
Now, we have an update on the Mars search. I want to show you some pictures that have been picked out by you, the viewers. We've had 60,000 people take part in this already. 60,000 people. 450,000 images of Mars have been explored by you in 24 hours. We should make it well over 500,000 tonight. This adds up to more than 15,000 square kilometres. That is an area you always have to have some size. It's 3/4 the size of Wales. When we did this in rehearsal at 4 o'clock, it was an area the edge of Cyprus. So we've gone from Cyprus to 3/4 of Wales. Can we make it all of Wales this evening? But this is one of the pictures. I mean, this is an interesting feature, never before seen, that was picked out by one of our viewers. That's on the surface of Mars. Here's another one. These are geological features. What is that? What is that? What are those bright bits? Is the sun catching it? Is it something else? It's fascinating.
And we haven't seen it. I mean, a conversation, a late night conversation with Brian May and ourselves in the bar after the show last night. If an alien spacecraft may have landed in this place, and you might spot it, that's not particularly likely, but nonetheless, if you go to the website, we'll give you a patch of Mars that you can look at and you can map. We really want you to join in because people of Wales are lost on Mars, and we need you to find it. Go to our website, click on the boxes that explore Mars, and all will come clear.
If you find Elvis, we'll give you a prize. Now, how did we begin to work all this out? Well, I just want to show you this one image. The answer is, of course, by looking at the universe, by observing it, by building telescopes. And this is a very famous, iconic telescope. It's the 20-foot telescope built by William Herschel in 1783. You had to stand on this stand to make observations. With this telescope, Herschel discovered 2 of the moons of Uranus, Titania and Oberon. He also discovered Enceladus, which we saw last night. With this telescope, one of the moons that we think may be a home for life.
Now, we like a crazy project on this show, and as a testament to all the early pioneers, we have decided to try to rebuild, essentially, Herschel's 20-foot telescope. And who better to take up that challenge of building such an instrument than Mark?
To find out just how Herschel made his 20-foot telescope, I've come to the Royal Astronomical Society in London, where Herschel's observations are kept, to meet Professor Alan Chapman, who I'm hoping can point me in the right direction. So, I guess the important question, I've got to build this. Have you got any plans or anything that I can actually take with me to help build this thing?
Not directly. We don't really have a lot of detailed drawings, apart from the sketches.
Okay, so I've only got pictures to work from.
Yeah.
Fabulous.
It's not just a matter of making the structure. It has to turn, and it has to go up and down, and to a very limited degree track, and you let the sky rotate in front of you.
So he used the telescope then more for discovery and mapping the sky?
He wants to fathom what he calls the length, breadth, depth and profundity of space.
And so he built bigger and bigger telescopes to see further out.
Precisely.
The telescope actually looks quite cumbersome. How did it actually work?
There are rollers, so the whole structure could be made to rotate. You would have certainly needed more than these 2 elegant gentlemen here. You would have needed some big, strong, beefy chaps to do all the heavy pushing and pulling.
So I need lots of poles, lots of ropes and chains, some big lads,
Big lads,
bit of ingenuity, and we can probably crack it.
And you could try it.
I hadn't quite appreciated how much effort Herschel had gone into to build the thing. And there's an awful lot more stuff that I've got to think about. So for me to build it and for me to get it working safely is going to take quite a bit of planning. I'm also going to need a lot of help. So I've come to the University of Derby, who have agreed to house the telescope, to meet the crack team who are going to help to make this happen. So hopefully I can see what Herschel saw. Structural engineer Mark Poole is going to lead the design, whilst the university staff and the local astronomy society are going to run and manage it after it's built. And they have a few tough questions.
It looks as though it's originally in wood.
Yes, it was.
Are we going to keep it in wood? Or?
My worry is if you can have this moving around on a base,
Yeah.
if you want to see a perfect image in the sky, you want the telescope to be still and not distorted.
Yeah.
Haven't you got to watch the centre of gravity as well?
Like, as you wind it up, it's going to become unstable.
How are you going to stop it sagging in the middle?
That's a very good question.
Also, how weatherproof is this going to be in terms of high winds? Could there be extra locking devices?
Looks like I've got a bit of thinking to do. Now, the engineers have come up with a design that looks a little different to Herschel's original. Instead of wood, we're going to build it out of scaffolding poles revolving around a central pivot. The telescope itself will sit in a cradle to support it, which can be winched up and down. Although it's been updated, it remains true to Herschel's principles. Now I'm against the clock to get this ready, so a solid base for the telescope to stand on is first on my list. We've got to know which way we're pointing the telescope so we can find objects in the sky. For that, we need to plot true north. So the local astronomical society is here to find it the proper way, with an atomic clock and the sun.
Yeah, I'm happy with that.
At local noon, the shadow thrown by a perpendicular stick will point north.
That is our north-south line.
And with some nifty maths, they can work out east, west, and the degrees in between.
If you are fasting, give you aid.
And to help us mark it out in style, the local primary school has arrived. After learning all about Herschel in their lessons, they've been inspired to paint a mural dedicated to him. How are your planets coming on?
Well,
Who's looking forward to looking through the telescope?
oh, me.
You?
Yep.
Yeah, we just need clear skies, don't we?
Yeah, just clear sky.
Which planets have we got here?
Uranus
And Saturn. So can you remember who discovered Uranus?
It was
William Herschel.
William Herschel. Is that a comet? Wow. So now the base is down and looking beautiful, it's time to put the construction plan into action. Now this is no ordinary scaffolding job. In order for the telescope to work, all measurements have to be totally precise. silly question, but how sure are you that you can get that absolutely plumb vertical?
100%.
Oh, that's excellent. I'm very pleased to hear that. I'm trusting you all. Shall we get started then?
Yes.
Yep, let's go with it. To see the whole night sky, Herschel needed a panoramic view. So the team attaches 12 wheels to the base so it can rotate. And construction of the frame that will support the telescope begins to take shape. Now Herschel's fell over 2 or 3 times, I think it was, so that's not going to happen here, is it?
Absolutely not. I think the worries are over. This is the part now where we're building. We've thought about all the things that could go wrong, and hopefully we've accommodated and taken on board all those issues, and we'll now have a nice structure that's be safe to use and no concerns.
I love the way you say the worries are over. With the key layers of scaffolding in place, it's time to add the specially crafted cradle for the 20-foot long telescope tube, which will hopefully stop it sagging in the middle. Well, it fits. Big no. And as it's put in position, you start to get a feel for Herschel's ambition and the sheer scale of what he was doing. Now there's just one thing missing, the actual telescope. I have no idea whether Herschel's drawings are going to give me enough information to actually see what Herschel saw through it, so there's still an awful lot to figure out.
Mark, that didn't look too easy.
No, it wasn't. Do you know, I still find it amazing the amount of effort that Herschel went through. And, you know, without the work of people like Herschel and others like him, we wouldn't be able to understand as much as we do about these amazing stars you can see behind me, like Orion and its beautiful 3-star belt. But, do you know, the setting up of the mount of the telescope was a little bit easier than I expected. The optics, well, and the telescope itself, that was a little bit more of a challenge, but you'll see a little bit more about that in a VT tomorrow. And after this show, I'll be heading down to Derby. If the weather's clear, then I'll be showing you just what you can see through the telescope.
This is important stuff. The lesson here is there's interaction between engineering and by inventing new instruments and what we can learn about the universe. Herschel, as we said, discovered Saturn's moon Enceladus with that telescope. You wind forward 100 years after Herschel was born, you get to Edwin Hubble. We've heard a lot about Hubble, the Hubble Space Telescope. I'm going to show you something now, the Hubble constant. I'm going to use my blackboard again. I'm going to move back through time, through the time of television to the 1970s. There's a thing called the Hubble constant. Right? This is what Hubble first measured, actually using a bigger telescope, the 100-inch telescope at Mount Wilson in California.
So what could you do with a 100-inch telescope that couldn't be done previously? What could he see?
Well, he was the first to see stars in distant galaxies, initially in the Andromeda Galaxy, and so he could see individual stars. He was the first to show the Andromeda Galaxy is not some kind of nebula in the Milky Way, but an external island of stars. And he went on in 1929 by making hundreds of measurements with high-precision telescopes to work out this number, which is called the Hubble constant, named after him. It is 70 kilometres per second per megaparsec. Now, a megaparsec is a strange thing. If you're an astronomer, you'll know what it means. It's a distance measure. That's just over 3 million light years. A parsec is 3.2 something light years or so. So this number maps, it encodes the expansion rate of the universe in it. It says that if you go about 3 million light years over there and look at the galaxies and average out their motion, then on average they're moving away from the Milky Way at 70 kilometres per second. Pretty slow, actually.
It is. Now, my favourite thing about this, by the way, is a little mathematical trick, and we're going to give this a homework for those who are so minded. That's distance and that distance, which means that if you got them to be the same unit, which is just the case of multiplying something, they kind of cancel each other out. And you're left with a number which is just in units of 1 over a second.
That is true, and this is a challenge. So what you have to do, in fact, tweet it at BBC Stargazing as soon as you've done it, 70 kilometres per second. Turn megaparsecs into kilometres. They will cancel out. You'll have a number, which is 1 over seconds. Invert that number. You'll get an age of the universe, which is something billion years. Send it in on Twitter. The first one that I see on Twitter, I'll buy you a pint.
There we go. Very enough.
Unless if you're over 18, I'll buy you a pint.
From this number, you flip it over, you get the age of the universe.
What I love about this is it's a measurement. It's a measurement. You can see how to do it. It's a simple measurement. This is how we first deduced or measured the age of the universe.
It's a beautiful thing. It's no wonder they named the most famous space telescope of all time after the man who came up with this fine thing. So let's go back over to Liz and find out more.
Thanks very much, Dara. Welcome back to JPL and the Operations Centre for NASA's Deep Space Network. It's from here that NASA communicates with many of its space telescopes, the best windows on the universe that we have. And if you want to look at the farthest reaches of our universe, you've got to be able to observe it from beyond the distortion of our atmosphere. That's why you need a telescope based in space. And probably the most famous of those has to be Hubble's images of the very early stars and galaxies. Now, Professor Richard Ellis from Caltech has been working with Hubble and has joined us now. Thanks very much for joining us. This iconic deep field field image of Hubble's that we know and love so well has recently been improved, is that right?
Yeah, this is a new image from Hubble. It's the deepest image that we currently have. And we're looking back 97% of the way back to the Big Bang. So this is pretty amazing.
Yeah.
And the 7 objects highlighted here in color are the most distant galaxies currently known, discovered from this image. And the one on the left there in red is the most distant object that we currently have seen. And it's being seen 380 million years after the Big Bang.
Incredible.
So we're seeing the universe in its infancy.
We really are. And can we now say these are the earliest galaxies? That's it?
No. We already know from the colors of these stars in these galaxies that the stars have got chemical elements in them that have been enriched within the galaxies themselves. So there are even earlier galaxies beyond the depth of this image.
Okay.
Now, Hubble has probably looked back as far as it can, but we now know that there are earlier objects. So it set the stage for further exploration of even earlier objects with more powerful facilities.
We need a bigger telescope. And in a bid to uncover those earlier galaxies and even the stars that came together to form them, NASA is currently building Hubble's successor. And I was lucky enough to be invited to the Goddard Space Flight Center to check out the latest stages of its construction.
And then I go,
The plan here is to look as far back as 13.5 billion years ago to solve the mystery of how the very first stars were formed. Stars that were the basis for everything else that's happened in the universe since and are believed to have been enormous, 300 times the mass of our sun. No one's ever seen them, but a telescope here is planning to change all that. These are the plans for NASA's most formidable time machine yet conceived. Called the James Webb Telescope, its 6.5-meter diameter mirror will let it see objects far fainter than Hubble can. It'll be the biggest telescope ever sent into space. And they've been busy building it for a decade. The mirror is too large to fly into space on any of today's rockets, so they've designed it to fold up into 3 sections. Each of the 18 mirror segments are precision-made from beryllium and coated in pure gold. And today, 2 more are just arriving. Critical spaceflight hardware. Don't you just love it? I would not want to be the guy maneuvering this right now. Far too nerve-wracking. Just don't drop it. Like everything else, these mirrors have been designed to be as light as possible by senior project scientist and Nobel Prize winner, Dr. John Mather.
We made it lightweight because it's the only way to get it up into space. The space shuttle could carry a very heavy load to a low Earth orbit. We needed to go much higher, so we're going up on a European rocket called the Ariane 5, and it can carry about 6,000 kilos, which is about half what the Hubble was. So we've got to make the telescope much lighter weight, even though it's bigger.
Each mirror weighs 20 kilograms, and they'll be assembled in a clean room, so nothing can contaminate their 1.32-meter diameter surface. It's not just its size that will give it the edge over Hubble. It's the kind of light that the Webb telescope is designed to see that will make all the difference. On its journey towards us, the light from the most distant stars and galaxies has changed. It's still traveling at the speed of light, but because the universe is expanding, the wavelength of that light has become longer, from visible to infrared wavelengths. And so to be able to detect that light, you need a telescope that's sensitive to infrared, and the Webb telescope is superbly sensitive to it. It can pick up the radiation from a bumblebee the distance of the moon. By giving the telescope's exquisitely sensitive infrared eyes, astronomers are on the brink of glimpsing our deepest origins in the birth of the first stars. Though for Dr. Mather, the most exciting discoveries will be those that we can't even begin to imagine.
Every time we build a big telescope, we get a surprise. And so nature just seems to be like that, our imagination is, even no matter how imaginative we are, there are things out there that we never guess.
Richard, you've been working on this area all your life. How important is it that we find those very earliest stars?
Oh, it's very important. This moment when the universe was bathed in light for the first time we call cosmic dawn. And locating this moment is really an important landmark in the history of the universe. And so figuring out when it happened is crucial.
And what are the implications if Webb actually does find those stars?
Once we know when this moment is, then we can start to come backwards to the present day and start to piece together how stars enriched the galaxies with the chemical elements, how the galaxies grew in size up to the majestic system systems that we see around us today.
And how does your research follow on? You know, if we find the stars, what happens next?
Oh, there's a lot more to do. We have to understand the physics of what's going on and how galaxies grow and assemble.
You're not out of a job just yet, Richard.
Unfortunately not.
Thank you for joining us. Join me later when I find out about some other NASA missions that are helping us to understand star evolution in much greater detail. See you in a bit.
Well, thanks, Liz. So, until the James Webb is launched, the deepest image of the galaxies we have is from the Hubble Space Telescope. And we should be able to see the same patch of sky outside with Mark right now. Mark, which patch of sky was the Hubble looking at?
Well, it was in a position in the constellation of Fornax, which is almost directly behind my head due south, but it's just below the trees, 10 degrees above the southern horizon. We've got a video that shows what it would be like if you were to take a journey in that direction towards the Hubble Deep Field portion of the sky. Now, the image took around 10 years to produce, and the final image was actually a combination of about 2,000 individual images. Quite stunning.
It is a stunning image, but whilst we can see back to the formations of the first galaxies and stars, we can't see all the way back to the first moments of the Big Bang, because it took light a while to get going in the early universe.
Yeah, if you look at the early universe, imagine it. Imagine when every galaxy you can see in the night sky now, the whole lot of the universe was crammed into something the size of your head, for example.
That's large enough now, to be honest. Yeah.
But very dense.
Yes.
So, and then the universe has expanded and cooled ever since. So the universe gets less and less dense and cooler. At a point around 400,000 years after the Big Bang, the universe had cooled down so much that electrons were able to go into orbit around the nucleus of atomic nuclei for the first time to form atoms. At that point, the universe became transparent to light. Light could travel through the universe unimpeded, and we can take an image. We can see that light now traveling from that place all those light years away. We've taken a picture of that image, and it is this very famous image. It's called the cosmic microwave background. Now, one of the scientists working hard to analyse this cosmic microwave background image is Joe Dunkley from Oxford University.
Joe, this is the first light in the universe. Is that what we're seeing there?
That's right. This is a map of part of the universe when it was only 400,000 years old. So in universe terms, that is a baby. It's the earliest light we can see. It was taken by a NASA probe called WMAP, which measured this faint glow of light that bathes us in all directions, microwave light, that's been travelling to us for about 14 billion years.
And what are we seeing here? Because it looks quite, there's a lot of differences here. There's a lot of features in this.
That's right. So the colour on this map tells you its temperature. The temperature actually is almost the same everywhere. But with probes like WMAP, we've managed to tease out these tiny variations across the sky. And so where you see it's being red, it's ever so slightly hotter than average.
Why ever so slightly?
Ever so slightly. It's only about a millionth of a degree.
Right.
The light we're measuring here is really, really cold. It's about minus 270 degrees. And then we're measuring tiny little variations, millionth of a degree on top of that.
So the measurement is the temperature fluctuations.
Yeah.
What do those correspond to?
Well, so they trace out, so you've got these ripples in temperature across that sky. They actually trace out tiny lumps and bumps in space. The space was almost completely smooth, but there were these tiny, weeny lumps and bumps. And they are actually the origins of all the stars and the galaxies that we see in the universe now.
Right.
We think they grew over millions of years until the lumps got big enough to form the very first stars.
So this image, it's the entire sky. So in every direction you look.
That's right, unwrapped onto a flat screen.
Tiny variations, and we're looking at the seeds of the galaxies. So without these little fluctuations, we wouldn't exist. We wouldn't be here.
That's right.
But I believe there's another mission now, Planck, isn't it, which is up there at the moment taking data.
That's right.
That gives a more accurate picture.
Yeah. So we've learned a lot from WMAP about what the universe is made of. But Planck, which is a European Space Agency mission, launched back in 2009. It's been operating beautifully. It's working at higher resolution and sensitivity than WMAP. This is a map of it right now. What you're seeing here is actually, in the purple, is actually our Milky Way galaxy. We're sitting in it and we're looking through it.
So that's essentially getting in the way of what we want to see.
That's right.
Is this what we want to see just at the edges here?
Yeah, exactly.
So we have to filter out the Milky Way and then we'll start seeing a refined picture of the one we've already seen.
Exactly. Yeah.
The question is, what is that going to tell us? Because I suppose, what is the origin of those fluctuations?
Exactly, the origin. So we have this crazy idea about what happened in the first trillionth of a second of the universe to make those fluctuations.
The first 1 trillion.
1 trillion, yeah. We think the universe expanded incredibly fast, faster than the speed of light, blowing up bits of space that are smaller than a nucleus of an atom into space larger than the sun in a trillionth of a second.
Yeah.
And we think that that's what made our universe the way it is today, but we're just not sure if that's what happened or not.
I find that quite remarkable, actually, that we make a measurement that you can link back to, well, events that may have happened a trillionth of a second after our universe began just by making this measurement. It's elegant, isn't it?
That's right, it's phenomenal. You can just trace it through all the way from this earliest time through to 400,000 years where we see this light, and then all the way through to today. And it's making so much sense. We're finding out what the universe is made of, how old it is, how heavy it is. It's really a wonderful.
It's wonderful. Thanks, Joe. We'll talk to you more in Back to Earth.
Joe, thank you. Thanks very much for that, Joe. We'll see you again. If you're hoping to get out and about after the show for a spot of stargazing, you're going to need clear skies. So for the latest on tonight's visibility, it's over now to Susan Powell in the BBC Weather Centre for tonight's stargazing forecast.
Evening. Actually, a pretty good chance of getting a good look at the sky this evening. We've got clear spells across many parts of the UK currently, but if you're planning on casting your eyes skyward in the south, you want to get on with it actually in the next hour or so, because we are expecting the cloud to thicken here as we go further on into this evening. Further north and you're up against some fog, so my two probably favoured picks for the clearest of the skies in the next few hours might be North Wales and the northeast of England. But if you're heading outside to look at the skies, just bear in mind that where we have got the clearest of the skies, the temperatures tonight are going to fall quite sharply, so we're in for a pretty chilly evening. Better prospects tonight though than tomorrow night. By tomorrow night, a lot of cloud across the UK. An old weather front in the east, a fresh one coming into the west, patchy outbreaks of rain. The clearest of the skies, I think, will be in a couple of slots in between those two weather fronts, but I think it will be pretty limited. So your best chances certainly are this evening. Perhaps tomorrow, not quite so great, but I'll be back tomorrow, of course, to give you an update on that. But for now, back to you two.
Thanks, Susan. Now, if you do have clear skies, get out there and take a look after the show, because even if all you're doing is gazing up with the naked eye, there's still a lot you can work out about the history of the stars above us. Here's Mark to explain.
On a clear, dark night, thousands of stars can be seen twinkling above our heads. To the untrained eye, it's easy to assume they're all the same, tiny white specks light years away. But in fact, many stars aren't white at all. Our nightly companions are many different colours, and those colours give us a clue to their life stories. Most stars appear white to us here on Earth because they are so far away that they are too faint to stimulate the part of the eye that lets us see in colour. If we could see as well as a powerful telescope, our view of the sky would suddenly turn technicolour. But when you know what you're looking for, picking out the colours of stars is fairly easy to do, even at a distance. And many are bright enough to be seen with just the eye. Well, let's start by looking at Orion the Hunter, one of the most recognisable constellations. It rises nice and high in the winter sky, so it's easy to spot. Now we start by looking for its famous three-star belt, which you can see just over my left shoulder. Move upwards to the left to find a star called Betelgeuse. It's not only the 11th brightest star in the night sky, but to the naked eye, it's one of the most colourful. Now you can't see this with our special low-light black and white camera, so here's what it looks like through our telescope. As we go out of focus, its stunning red colour becomes really prominent. Well, if we go back to the belt stars and start at the top star and drop a line down towards the lower right-hand corner, we spot another fairly bright star in Orion, and it's called Rigel. Here is Rigel out of focus through our telescope. You can see it's a vivid blue colour. Both Rigel and Betelgeuse are what are known as supergiants. They are amongst some of the brightest and most massive stars in the night sky. But why is one red and the other blue? The colour of a star can tell us how hot its surface temperature is, but not in the way you might imagine. Now we think of hot things as red and cold things as blue, but the hotter a star is, the bluer it looks, and the cooler the star, the redder it glows. So Betelgeuse is actually colder than blue Rigel. Now with a simple chart like this, we can actually tell how hot the stars are. So I'd say Rigel is actually a bit more of a blue star than a bluey white star, which means its temperature is at least 10,000 Kelvin, which means it's a burning furnace with phenomenal amounts of energy. Now at the other end of the scale is Betelgeuse, which is a red star, and that shows us that it's less than 3,700 Kelvin, so it's much cooler. One of my favourite colourful objects to observe is a star called Almach in the constellation of Andromeda. Now to find Andromeda, you first need to find the square of Pegasus. At this time of year, it rises directly above our heads. Start with the brightest star in the square. This is called Alpheratz. It's a hot blue star with a surface temperature of around 13,000 Kelvin. Now if we imagine a line moving upwards from Alpheratz, we reach another bright star called Mirac. It's a much cooler orange-coloured star. If we continue even higher, we come to Almach. With the unaided eye, it looks like a single white star. But if we look at it through a telescope, it transforms it into one of the most stunning objects in the night sky. Almach is a double star. It's made of a hot blue star orbiting with a larger, cooler, golden companion. And when you see these two stars close to each other, it makes their contrasting colours all the more striking. Observing the colours of the stars can take a little practice, but it's well worth the effort. And the more you discover about the colour and other characteristics of the stars, the more they'll reveal their secrets to you. Well, I'm here with some of the younger members of the Liverpool Astronomy Society. Now, Joe, you've been into astronomy for a couple of years now. Do you remember the first time that you saw the colour in the stars?
Yeah, it was a star and it was low on the horizon. It was just flickering from red to blue, and I know that's not the real colour of the star, but that's what started me on the road to learning about them.
And they look really quite beautiful, don't they?
Yeah.
Now, Harriet, what did you think the first time you saw some colourful things in the sky?
It was like really cool because I thought all stars were white, but then I realised that they're like kind of all different colours depending on their age and their temperature.
And that is the case, that it's the temperature that affects that. It's not just the temperature, of course. Now, of course, there are other things, aren't there? And there's the planets, for example. Have you seen any colour in the planets?
I think I saw Jupiter. It's got like an orangey brown, a white, and there's like a red dot, and it's a volcano.
That's right, there's a
It's
big
like
storm.
yeah.
There's a big storm on Jupiter, isn't it? Well, thanks very much for that, guys. We'll let you get back to observing, and we'll go back now to Brian and Dara in the studio.
Okay, big debate going on here about what the colour means. Does it mean the temperature? Does it mean more than that?
First of all, Mark, it is just the temperature. The young lady there was absolutely correct.
It's just that why it's at that temperature can differ.
Yes, the reason why. So we've got a picture of Proxima Centauri. It's what's called a red dwarf star. It happens to be the closest star to us. It's only about 4 light years away. It's part of a triple star system with Alpha Centauri A and B, very bright stars in the southern sky. This is red, and it's red because it's cool on its surface. That's because it's very small. It's around about a tenth of the mass of the sun. The payoff for it, although it's small, is it will burn for many, many, many billions of years. But here's another famous red star, and I've just can you believe I've messed up my thing again? Oh, go
Tell us
on.
the name of
This is this picture you can't see now unless they can fade it in. Is a star called there it
there we
is.
go.
This is Betelgeuse or Betelgeuse. Now this is a red star for a different reason. It's a very, very, very large star indeed. Many, many thousands of times the mass of the sun. You could fit most of the solar system in there. And even though it's 600 light years away, you can see that we've got a picture of sunspots on the surface of Betelgeuse or Betelgeuse there. Now that star has only been alive for less than 10 million years. It's burning its fuel so voraciously. Its surface is cold because it's very, very large, and so it's a long way from the core. That star is very variable. Very famous star, by the way, the top left in the constellation of Orion. You can't miss it on a clear
Things
winter's
might get more dramatic for that star at any point.
because it's burnt up all its fuel, all its hydrogen fuel already. It's already burning helium. It will build the heavier elements in its core. It will run out of fuel. It will collapse, and it will explode as a supernova explosion. This is an artist's impression of what that would look like in our sky. And this, quite honestly, could happen tomorrow. And certainly tomorrow in astronomical terms. Betelgeuse is on borrowed time now. And that will look like a second sun in the sky. So
For how long will we have this in the sky?
It'll glow for about, 2 weeks like that. It will be the most spectacular sight, as I said, a second sun. And what you're seeing there is the distribution of the elements of life out into the universe.
Because we're overdue a supernova in the Milky Way.
We're overdue on it. On average, you get about 1 supernova per large galaxy per century.
Okay, we have because we have an animation. What was the very famous one?
The famous one's a crab.
The Crab Nebula.
Yeah, and this is the animation.
And this is an animation. It happened in 1054. It's written about by Chinese astronomers.
Yeah.
That is an animation what it would presumably would have looked like, and we'd been left with the Crab Nebula at the end of it.
Yeah.
That furnace basically was where all the heavier elements are built.
Well, again, it's a beautiful thing to look at with any small telescope. It's a spectacular thing in the sky. But what we're looking at here, well, we've got an image actually that we took earlier on tonight, I think.
Can't see it now. I think it's under behind cloud.
There it is.
That is it.
So that's a small telescope. It's a misty patch. What you're looking at there, though, is the elements of not only carbon and oxygen that were cooked in the heart of that star, but elements like gold. Anything heavier than iron cannot be made in the centre of a star. It is made only in those explosions for a few minutes per century per galaxy. And that is why gold, platinum, uranium, tin, all those things are expensive, because they're rare, because they're made in those explosions. And that's what so go out and look at the Crab Nebula tonight. You can do it. Absolutely beautiful.
So just as the earliest light we can see teaches us about the origins of the first stars and galaxies, studying the explosive death of stars ultimately tells us how we got here. Liz Bonin is standing by for us at NASA with some of the pioneering scientists leading this research.
Thank you very much, Dara. I'm with Professor Fiona Harrison from Caltech, Principal Investigator with NASA's NuSTAR Space Telescope, launched just over 6 months ago. Fiona, thanks for joining us. NuSTAR has got us this image of a supernova remnant in the Cassiopeia constellation, which is just incredible. And am I right to say that NuSTAR is the only telescope that could get us this image?
That's right. So NuSTAR is the very first high-energy X-ray telescope that can actually focus. And so it's making images that are more than 10 times crisper and more than 100 times more sensitive than anything we've had in this part of the spectrum. So what you're seeing here is material that was made inside the star and spewed out in a supernova explosion. But what NuSTAR is uniquely able to do is image the radioactive material that was created in the thermonuclear explosion. And in particular, an element called titanium-44, which will eventually decay into calcium and could end up in our bones.
Excellent. And understanding this gives us a better understanding of how stars explode?
Yeah, that's right, because this radioactive material is created in the core of the explosion, and so its distribution is very sensitive to whether that explosion was spherical or lopsided. And that tells us how stars explode.
Wonderful stuff. Thank you very much, Fiona. Now, one of the telescopes that is communicated with the Deep Space Network is Spitzer. That's been working for nearly a decade now. And Neil Turner is an astrophysicist working with the Spitzer mission. Thank you very much for joining us, Neil. Now, Spitzer looks in the infrared. It can peer through all the dust and gas of newly forming stars. So when all the material from supernovae begins to form into stars, Spitzer can give us images like this. So to talk me through what we're looking at here.
Well, we're seeing a heaving cauldron where gas and dust are being thrown back and forth by young stars. In particular, massive stars are forming here. You can see a bubble being blown here, and also here by the prodigious light and the winds coming out from these stars. Eventually, it's going to shred the cloud and stop star formation here.
So you're learning a lot more about how that process actually comes about. And what about planets coming into formation around a star? Can Spitzer tell us more about that?
Spitzer is great at seeing the gas and dust orbiting young stars because they're warmed by the starlight.
Yeah.
And so in particular, just yesterday, one of the teams announced that they had found actually a second asteroid belt around Vega, second brightest star in the northern night sky. That's exciting because we already knew about an outer one, and now Vega looks like an analog of our own solar system, where we have an inner and an outer belt sculpted by the planets, and so almost certainly there are planets around Vega.
Fantastic stuff. Thank you very much, Neil. So in our journey through the history of our universe, these missions are teaching us so much more about the cycles of star death and star birth, and how all of that works together to understand how our universe is shaped. We'll also find out a lot more about how and from what our own solar system came to be, how we all came to be made of star stuff. Now, tomorrow, we are leaving this wonderful place. We're heading deep into the desert to this Goldstone, part of the Deep Space Network, and I'll be finding out how scientists are tracking near-Earth asteroids. We will see you tomorrow.
One quick bit of business, by the way. Thanks to your guesses on Twitter. No, the answer isn't 13.75. That is the actual age universe, but what we gave you is a bit of an approximation. Should have come out of 15 billion. You owe a point to Guy Andrew Murray.
Right. I'll see you in the pub.
Okay, fine. Now, what have we learned in our history of the universe? We have found the first light that emerged after the Big Bang. We've seen the formation of stars. We've seen the formation of planets and indeed of ourselves, which probably just leaves the last final bit to
I want to wrap everything up now with Professor Ed Copeland, who's a cosmologist from the University of Nottingham. Ed, thanks for joining us. The question is, what is the fate of the universe? I don't know.
Okay, thanks for coming along, Ed.
But I've only come from Nottingham, so it's not so far. The best you can do, because you're needing to look into the future, is to base it on whatever models that you have. And we've got a series of models that are consistent with the data, and so you can project them forward and see what they give. So there's sort of 3 scenarios I can come up with right now for you. In your VT, you had a thing about dark energy driving the acceleration of the universe. Well, imagine that dark energy is constant. That's the cosmological constant, which, by the way, is a nightmare for particle physicists to understand why it's got this value.
We'll talk about that in Back to Earth.
Oh, okay, great. But if it is driving the universe, then the universe is accelerating, so distant galaxies are accelerating apart, and so our line of sight will just... These galaxies will disappear before us over many billions of years, and gradually it'll just look like an empty universe with these things all spread out. And we won't be able to see anything.
You would see no stars in the sky.
Well, probably we won't even be here by then.
We won't, but that's
I was going to go, woohoo! So the other two, there's another one which is, imagine the dark energy is actually, the density of that is actually increasing over time, so it's getting more and more dominant. Then things are a bit more dramatic. The data doesn't suggest it should be like that. It's the first one that I just described as the best fit. But if it is, then actually the acceleration is even more rapid. So then not only do the galaxies move apart, but then they began to split apart. And the galaxies split apart, and then the constituents of those galaxies split apart, the atoms split apart, and you just get all the fundamental particles thrown across the universe like an angry child throwing their toys out of the box, right? Filling the universe with these particles, and that's the end.
Again,
of that.
not wonderful.
Not wonderful.
Do we have a happy ending?
There's a happier ending, and that is in the case where the dark energy is a transient feature, and so it's driving the acceleration now, but maybe it's changing with time, and it actually decays, a bit like in the early inflation that you described at the beginning of the program. And there what will happen is that energy in the dark, that's stored in the dark energy, goes to create particles, create radiation, the universe reheats again. And now we're back to a kind of a scenario at a much lower energy scale, like we used to talk about, which is one where the universe is evolving with radiation and matter, and now the curvature of the universe becomes important in determining the ultimate fate of the universe.
In so many ways, that's the most palatable.
Yeah,
of
I
the
think
3.
that's
and it's still not entirely palatable, is it?
Yeah, that's right. It's
also the least likely.
At the moment, it looks like the cosmological constant is.
Well, we're going to talk about a lot more of this, then, can't we?
I think so. Yeah, the show after this, we'll definitely have more time to talk about this. For one final time, however, tonight, let's go outside to Mark.
Well, it's still a gorgeous clear sky. Everyone's gone indoors now for the start of Back to Earth. But if you've been inspired to look up at the sky, there are loads of resources that you can download off the website, along with details of hundreds of stargazing events up and down the country. Just go to bbc.co.uk/stargazing. And if you want to get hold of one of our stargazing guides, then details on the screen. They were made in conjunction with the Open University. It's well worth getting hold of one of those. So back now to the studio.
Okay, that's the star guide there, but really, at the very beginning of the show, I promised to ask Brian the ultimate question. What happened before the Big Bang?
Well, here's the thing. There may have been a before the Big Bang. The universe may have existed for an infinite amount of time before the Big Bang. We'll talk about that, I think, a little bit more in Back to Earth. Or time may have begun at the Big Bang. So the answer is either the universe has been here forever, or it hasn't.
It's fantastic, isn't it? This is why we get him on this thing, you know? that kind of fabulous, incisive. Anything could have happened, and anything may well happen, all right? That's what we're giving you.
No, but I tell you what, there's a lot of physics in what I said there, and we're going to discuss it all in about 1 minute.
In about a minute, we'll be back here, we'll expand on this. We may even get a proper answer. See you in a few minutes.
See you in a bit.
That was great.